Section 6.6 of your textbook covers the topic of rational equations. A rational equation is an equation containing one or more rational expressions. And the process of solving rational equations is very similar to the process of solving an equation containing fractions by first multiplying both sides by the least common denominator. Let's review this process using the equation shown on the slide. Notice that the LCD of 3, 2, and 4 is 12, so we'll begin by multiplying both the left-hand side and the right-hand side of our equation by 12. Applying the distributive property on the left-hand side, we have 12 times 2, or 24 over 3 times x, and then plus 12 over 2. Distributing on the right, we have 12 times 5, or 60 over 4 times x, minus 10 times 12, or 120. Now the real advantage of multiplying by the LCD like this is that we can clear the fractions from the equation. Notice that all the fractions we've written down can be simplified to whole numbers. For example, 24 over 3 is simply 8, so our first term is 8x. And then 12 over 2 is 6. On the right-hand side, 60 over 4 is 15 times x, and then minus 120. Now this equation without fractions is fairly easy to solve. We just want to isolate the variable. Let's subtract 8x on both sides, and also add 120 on both sides. This results in the equation 126 equals 7x, and then we can divide both sides by 7 to obtain the equation 18 equals x. So our solution set contains one number. 18 is the solution of the equation. We could verify that by checking it in the original equation and noting that it makes the equation true. Let's quickly describe the steps to solving rational equations, and then we'll look at some examples. There are 4 basic steps. The first step, which is extremely important, is to list restrictions for the equation. We must remember that numbers that make a denominator equal to 0 can never be solutions of our equation. Second, we will clear fractions using that process of multiplying both sides of the equation by the LCD. Third, we will solve the resulting linear or quadratic equation using the appropriate methods. And fourth, we will write the solution set, again, remembering that numbers that are restrictions cannot be solutions. Let's turn to some examples. Our first equation is x plus 6 over x equals negative 5. Since the only denominator in this equation is x, the only restriction is that x cannot equal 0. That's the only value that would make a denominator equal to 0. X is also the LCD, so we can start by multiplying both sides of the equation by x. On the left-hand side, x times x is x squared, and then x times 6 over x would be 6x over x. But notice that we have an x in the numerator and in the denominator, so as expected, we can simplify those, and our equation has been cleared of the fraction. On the right-hand side, we just have negative 5 times x. Note that this is a quadratic equation. We can see that from the x squared term, so we need to set one side equal to 0. We can do that by adding 5x on both sides to obtain x squared plus 5x plus 6 equals 0. Now factoring the trinomial, we have the quantity x plus 3 times the quantity x plus 2 equals 0. Remember that we can use the zero product property to state that either x plus 3 equals 0, which would mean x equals negative 3, or x plus 2 equals 0, which would mean x equals negative 2. Now before writing our solution set, we need to compare those two solutions to our restrictions. In this case, the only restriction was that x cannot equal 0, so it is possible for x to equal negative 3 or negative 2 in our original rational equation. Therefore, our solution set contains both of those numbers. Let's move to the second example. In this case, there are two rational expressions, but both of them have the same denominator, x plus 2. Therefore, the only restriction is that x plus 2 cannot equal 0, which means we want to make sure that x does not equal negative 2. Now we can start by clearing the fractions by multiplying both sides of the equation by the LCD, which is that binomial x plus 2. On the left-hand side, x plus 2 times 1 is simply x plus 2. And then we're multiplying x plus 2 times that rational expression. So x plus 2 times 3x over x plus 2. As expected, we can see that the x plus 2 in the numerator cancels with the x plus 2 in the denominator. Similarly, on the right-hand side, we have negative 6 times the quantity x plus 2 in the numerator. But in the denominator, we also have that binomial x plus 2, and we can remove the common binomial factors. So our simpler equation is x plus 2 plus 3x equals negative 6. Now this is a linear equation, so we're going to isolate the variable to solve it. First, let's combine like terms. On the left, x plus 3x is 4x. Then we will subtract 2 on both sides. And finally, we'll divide both sides by 4. So the solution of the linear equation is x equals negative 2. However, note that in our rational equation, a value of x equals negative 2 would create a denominator equal to 0, resulting in expressions that are undefined. So while x equals negative 2 can be a solution of that linear equation that we found, it cannot be a solution of the original rational equation. So we cannot include it in our solution set. And our solution set then is empty. It has no numbers in it. This rational equation has no solutions. Let's do 2 more examples. In problem number 3, note that we have 3 rational expressions. And also note that on the right-hand side, that denominator, x squared minus 25, is a difference of squares. It factors into the quantity x plus 5 times the quantity x minus 5. And so we can use that pair of binomials as our LCD. So we're going to multiply both sides of the equation by both x plus 5 and x minus 5. And of course, as we do so, we need to keep in mind the restrictions on this problem. X cannot equal positive or negative 5, because both of those values would make a denominator equal to 0. Now we can save time with our multiplication if we simplify as we go, remembering that the goal of multiplying by the LCD is to clear fractions. So in the first rational expression, notice that there would be a factor of x minus 5 in the numerator and in the denominator. So really all that remains is 3 times the other binomial factor, which is that quantity x plus 5. In the same way, in the second multiplication, we'll have an x plus 5 in both the numerator and the denominator, and those will cancel out, leaving us with 1 times x minus 5. And on the right, there will be a factor of x plus 5 and x minus 5, both in the numerator and the denominator, so we can cancel all of those binomials out and just result in 2 on the right-hand side. Now we can solve the linear equation. Let's distribute. So we have 3x plus 15 plus x minus 5 equals 2. Combining like terms, we have 4x plus 10 equals 2. Subtracting 10 on both sides, we have 4x equals negative 8. And dividing by 4 on both sides, we have x equals negative 2. Comparing that to our restrictions, we see that there are no restrictions in our list of solutions there, so that negative 2 can remain in our solution set. It's a solution of the original rational equation. One final example, in problem 4, note that there's only one common denominator here, the binomial x minus 1. So we would say that there's one restriction, x cannot equal 1, and we would multiply both sides of the equation by that binomial x minus 1. Again, let's cancel as we go. On the left-hand side, the binomial x minus 1 in the numerator cancels with the binomial x minus 1 in the denominator, so we're just left with x squared. And on the right-hand side, once again, those binomials cancel, so we're just left with 1. This is a quadratic equation, so we have to proceed by subtracting 1 on both sides to set the right-hand side equal to 0. Factoring our difference of squares into the quantity x plus 1 times the quantity x minus 1 results in two solutions of this quadratic equation. Either x plus 1 equals 0, which means x equals negative 1, or x minus 1 equals 0, which would mean that x equals 1. As we look back at our restrictions, we see that even though there are two solutions for this quadratic equation, one of them is restriction from the original rational equation. So when we write our solution set for the rational equation, we can only include the solution of negative 1.